Hello, guys. I hope all of you are doing great. Today, we're going to cover a new topic in our course, which is robot forward dynamics. All right. Before we get into it, I want to let you know that the exam 2 will take place on Monday, December 7th at 6 p.m. And I have put an announcement and I mentioned everything that is going to be covered in that exam. So make sure you read that. Um, just an overall, it will still cover transformations. So you are still responsible for understanding the transformations, but it will also cover the additional stuff that we did, such as differential kinematics, robot Jacobian, how do you calculate the Jacobian based on both the analytical and the graphical method, what is the interpretation of the Jacobian, and finally, a little bit of inverse kinematics that we have been working with. It will not cover inverse dynamics, neither forward dynamics. These are going to be mostly for the final exam. All right, so why do we need robot forward dynamics? I'm going to come back a little bit, take a brief step back into, where we have been going with this course, right? And I want to do that on a very simple example. If I have a 2 degrees of freedom robot, right? Very simple robot. And if I would like to move this robot or the end effector of this robot along, some trajectory, right? And I know this trajectory as a function of time, basically. I know the x of it and then the y of it. So far, what we have been doing is we have been able to solve the inverse kinematics, right? And if I have this theta 1 here, and this guy is theta 2 there, I'm actually able to solve theta 1 and theta 2 for any pose, right? And if I have a pass, right, as a function of time, it means that I can actually use inverse kinematics to solve theta 1 as a function of time, right? And also theta 2 as a function of time. So this is using inverse kinematics. So inverse kinematics will give me these. And once I have these, it's very simple. I can actually differentiate this, this could be like an array. I can actually obtain theta 1 prime as a function of time. And if I differentiate this one more time, I will actually obtain the acceleration as a function of time. And same thing for theta 2. Basically, I can obtain theta 2 prime as a function of time. And if I differentiate it further, I can actually obtain the angular acceleration of theta 2, right? So this is basically from inverse kinematics. Then what we did is we took all of these guys and we use inverse dynamics, right? ID, inverse dynamics. And with inverse dynamics, what we did is we separated this robot, right? We kind of expanded this robot and, we put the forces on it, right? We said, okay, I have, torque on the first joint. I have, OX, OY, and on the second link, etc. I have, O1X, I have O1Y. I have equal and opposite torque, T2, etc. But what we did is we actually used the information from inverse dynamics, mainly theta 1 double dot and theta 2 double dot, right? And we said, this guy, Newton's law, F is equal to ma. So basically at the center of gravity here, we're going to have m agx, and then we're going to have m agy, and we have ig alpha 1, right? Alpha 1 has to be theta 1 double dot. So here, be very careful that theta 1 double dot, or the rotational inertia, is always in the same direction as the gross direction of theta. So this is my theta, this is a fixed line, so theta 1 is going to be increasing like that, all right? So you always have to actually put this rotational inertia moment is in the same direction as the increasing direction of theta. Same thing for link 2. So we use inverse dynamics to be able to compute all of these, given that we assume the movement. So given that the movement has already occurred along this path, what are the torques that are on every joint, and what are, the forces which are acting on all the motors. Okay, so inverse dynamics is great if you actually have a path, but it doesn't actually tell you how to actually command the torques, right? Well, it will basically tell you how to command the torque in a sense, what should be the torque, but most of the time, the mass here, the IG is not very accurate, right? Or the links, may not be 100% exactly what you think your computation is, so you will actually have errors. So you can't use that if you want to control the robot. You can't use this pass, for example, and then solve for the torques as a function of time, and then you say, okay, I'm going to put these torques, and then I'm going to expect the robot to actually follow exactly this curve. Why? Because of the inaccuracies that you will actually have. So what we do need, we need to obtain forward dynamics of the robot, and we need to be able to relate the torque that is applied on the first link, on all the links basically. We need to be able to relate all the torques. So here T1, I have T2. So I need to be able to relate T1 and T2 with, with the accelerations of all the links on the robot. We can start doing that, and then we'll begin as we're going to analyze this on a 1 degree of freedom. And then we'll see how this actually gets applied to more than 1 degree of freedom very easily. So again, forward dynamics is we're going to find the relationship between the torque and the angular accelerations of that. Here we assume we know the angular acceleration, and then we try to solve for the torque. Now we're going to do the other way around. All right, so here is what we will do is I'm going to start with very basic example. I'm going to start with a pendulum, right? An actuated pendulum, basically. All right, so this is my pendulum. And what I'm going to do is I'm going to assume that I actually have a torque applied on that pendulum. And, basically we're going to have this angle theta that I'm using as a reference. And basically what I would like to do is I would like to find, torque, what is angular acceleration based on that torque, right? So if I have a torque as a function of time, what would be the angular acceleration, right? So there are two ways that we're going to do, two methods. The first method is using direct method, which is basically F equal to MA. We're going to apply that in its most basic element. And then number two, we're going to use the energy method, which is based on Lagrange. So this is Newton, this is like Lagrange. Okay, so how do we do that? So direct method, we're going to apply basically exactly kind of what we did before. So we're going to put the forces, and then we're going to put the inertial accelerations, and then we're going to find the relationship between the torque and angular acceleration. So how do we do that? So let's do a free body diagram on this. So how does a free body diagram look like? So obviously we have a torque applied on it. We have our reaction, OX. We have OY. And then we have the weight, always applied at the center of gravity. So this guy is mg. And on my inertial diagram, right? And obviously, this guy is theta right here. On my inertial diagram, basically, what we said we're going to put is, we have two things, right? We have the acceleration, or the mass times acceleration of the center of gravity, right? Which is how basically we know that this guy is rotating about here. So we only have this guy, right? Mass times what is the acceleration here. So this guy is pivoted about that. It's rotating about the center. So it only have tangential acceleration, right? Which is L theta double dot, right? And because this has a geometry, it's a rigid body, it's not a point mass. If it's not a point mass, basically, if it was a disk or a sphere or whatever it is, you will actually have rotational inertia, which is IG theta double dot. All right. If this guy was a point mass, then obviously the radius would be zero, IG would be zero, then this guy will vanish. But if this guy has any sort of dimension or a radius or whatever it is, then it will actually be G theta double dot. And make sure you always, this rotational inertia is always in the gross direction of theta, right? So this is my fixed line, and I'm tracking the position of the pendulum with respect to this absolute reference. Then IG theta double dot is in the same direction as this guy, gross direction of theta. Okay, same thing for the acceleration. So we're going to assume that theta is increasing. What would be the acceleration of this guy? Okay, now we need to continue, and then we need to find the relationship here. So the best way is, so in fluid dynamics, I'm not really interested in OX and OY. I'm only interested in finding a relationship between the torque, where the motor is located, and the angular acceleration. So I'm trying to relate, how will that thing accelerate if I apply torque? right? A positive or a negative torque. And later on, we'll actually use that to be able to control the pendulum and then force it to go into any random position. So the best way is actually, I'm going to sum the torques about 0.0, and we can actually use that to be able to solve it. So we're going to sum the torques, and I'm going to assume, this is my, counterclockwise direction to be my positive direction, and then about 0.0 is going to be equal to, so on this figure, I'm going to have only torque. So OX and OY will not create any torque because they intersect the axis of rotation, which is located at 0.0. So we have T. Now mg is actually creating a negative torque about 0.0 with a moment arm of L sine theta, right? Obviously, you assume that the link length is L, right? So T minus mg L sine theta. So mg has a moment arm of L sine theta about 0.0. On the right figure, whatever that I did, I'm gonna do it here again. So what is the moment arm of now this inertial force? So this inertial force is located about that distance L, right? So I'm gonna multiply this force by this moment arm, which is L. So ml theta double dot times L is gonna be m L squared theta double dot. And then this is already a moment, so I will just simply add it. Okay. Now I can rearrange that. So this is my input torque. That's gonna be equal to m GL sine theta plus, so I'm gonna factor out my theta double dot. So theta double dot IG plus ML squared. So this is really my forward dynamics relationship, right? So given a torque, what is the acceleration? So the best way now is, I can actually use that to be able, so I'm going to put here, I can now actually solve for the angular acceleration as a function of torque. So what is that? Let me just a little bit. Okay, so I can actually solve for my angular acceleration. I want to say theta double dot is going to be equal to what? Torque minus m GL sine theta. And I'm going to divide that by this guy. Notice it is rotational mass, right? And they actually have the same unit, right? Which is in kilogram times meter squared. So IG plus ml squared. So if I actually know the torque as a function of time, right? This is actually a second order differential equation of motion, right? So this would be as a function of time, but now it's a nonlinear equation because I have sine theta. Now, if this was much smaller motion, then you can estimate sine theta to be equal to theta and then solve it. But now if you have a sine theta, it will be a non-linear differential equation and will not be able to solve it using basic techniques. You'll have to use more advanced techniques. One way that I personally like to use is using the numerical technique, which is very basic and very easy. Just get the acceleration from the equation, solve the acceleration in terms of external forces which are applied on your system and the current position of the system. So now I actually have the acceleration. So whatever torque is at that geometry, I have particular angular acceleration. So given that I have to double dot, how can I find the position, right? The goal of solving a differential equation of motion is to find the position as a function of time. But now we don't have the position directly, we actually have the acceleration. So the best way is to actually integrate the acceleration. And when you integrate the acceleration first one time, you will actually have the velocity, which is theta prime. So theta prime is actually over a very small increment dt. So I can simply do that. So theta prime is equal to my acceleration times very small step plus my previous velocity. So now I actually have the velocity. If I want to obtain the position, I will do it one more time. So theta is going to be equal to theta prime dt plus theta. So all I really need is run a loop about these guys. So I will have some initial initial values for theta, initial values for theta prime, right? Based on that, so I will start with some known theta and known theta prime for this. So it could be so this guy would be at this theta, and then it has a theta prime like that, for example. Let's call theta prime 0. So theta 0 and then theta prime 0. I will start here, right? And whatever torque that I have as a function of time, I can solve my angular acceleration, right, based on theta 0, right? So I can obtain this theta double dot. Then I can jump here one step, and then I can find my theta prime. So whatever value I have here multiplied by dt, then add my previous velocity before the loop, and then I can find my position by integrating this guy also numerically. So if you continue and then doing that, basically you will actually solve theta, right, as a function of time instantly, basically. So this is one way of doing that. What I want to ask you guys to do is be able to get to this point basically with forward dynamics. You will actually have, I already posted an assignment, so you will actually be able to apply this technique on the assignment. All right, so this is my first method. The second method is going to use the indirect method, which is the energy method. And that will actually use Lagrange. And here is how we actually do that. So now we're gonna cover the energy method. All right. So with the energy method, basically I'm gonna do the same thing that I had, right? Which is my inverted pendulum. Not inverted, sorry, it's a regular pendulum. And I did actually have a torque applied on here, right? And we know this guy has a mass m, right? So with the energy method, what we're going to use is we're going to use what we already referenced, which is the Lagrangian dynamics. So what we will do is we're going to initially define our Lagrange. Lagrange actually is nothing but the difference between the total kinetic energy of the system minus the V, which is total potential energy of the system. All right. All right, and then when we want to obtain a differential equation of motion, here's what we'll do. We're gonna differentiate this guy. So we'll do the partial derivative of Lagrange with respect to the velocity, and then we apply this on every degree of freedom. So this is my theta, let's say. So what I will do is I'm gonna do differentiate Lagrange with respect to theta prime. So d over dt of partial derivative of Lagrange with respect to the velocity of the first joint. So I could have 5 or 6 joints, and then I can do this over and over again. Lagrange will not change. So this is for the whole system. But when I obtain the equation of motion for individual joints, I will actually differentiate with respect to, so this guy would be theta prime 1, for example. Okay, let's continue. So minus dl over d theta. Okay, equal to the non-conservative forces which is applied on a system. In that case, you will actually have a torque. All right. So this is my Lagrange for the whole system. And this is equation of motion for my first degree of freedom, right? Which is, in this case, I only have one, so I'm just keeping it at theta. But if I have actually multiple, I will have to write this one for the first degree of freedom, this one again for another degree of freedom, but I will only change theta prime here and then theta. Well, let's do that. Let's begin by let's begin by finding T. What is the kinetic energy of the system here? So the kinetic energy of this, mass here is equal to, always, it will have a rotational component and a translational component. So the translational component is going to be 1 over 2m velocity of the center of gravity square plus 1 over 2 moment of inertia about the center of gravity multiplied by theta prime square. So somehow I have to calculate the velocity of the center of gravity here. And I think most of you can quickly see that this is nothing but, tangential velocity, which is equal to L times theta prime, right? And, if you, so basically it's like that, right? So this is my velocity, L multiplied by theta prime. Or if you want to use your previous technique that we have done, right? I can, for example, I could put a frame X and Y, and I can express the position of the center of gravity, and then I can differentiate that, right? What would be the position of my center of gravity? It's going to be equal to L sine theta. How about YG? It's going to be equal to L cosine theta, right? Or minus L cosine theta. Now, what is x prime of G is going to be equal to L cosine theta multiplied by theta prime, right? Now, how about y prime G is going to be equal to minus L sine theta multiply that by theta prime. So how do I find the velocity? It is simply the square root of Vx squared plus Vx prime squared plus y prime G squared. So my velocity of G is equal to square root of x prime G plus y prime G squared, which is equal to square root of, so L squared cosine squared theta multiplied by theta prime squared plus L squared sine theta squared multiplied by theta prime squared. So you see that cosine theta squared and then sine theta squared can be factored out to be equal to 1, and then you will only end up with L theta prime. So, if you don't see it directly that this is translational, you can just do the basic stuff that we've done, right? So simply express xg, yg. And this is the beauty of Lagrange, as you will see later, is that once we express the kinetic energy, it's very easy using MATLAB because we can actually put a frame. So if you have, multi-link robot, you will simply put the frame at the center of gravity, find your homogeneous transformation from the start to finish, and the homogeneous transformation will already incorporate that position of the mass, right, or the center of gravity. So we can differentiate that to quickly obtain the total kinetic energy of the system. Yeah. Okay, and then this is a rotational energy. In this case, it is very straightforward. So we're done with T. Now let's look into our potential energy. Okay, so we've got that. Okay, let's do it here. So what is the potential energy here? So just very quickly here. So the potential energy is, you can choose anywhere that you want for your reference, right? You can choose in the middle, at the bottom. Might be a good idea to choose to use the frame, right? The base frame to be, your Y here basically will actually give you the potential energy of the system, right? So what is my potential energy here? So we said it's equal to V. So my potential energy, if I choose the top, it will be minus mg L cosine theta, right? Then what is my, just draw it again here, that this is my theta. So my potential energy with respect to this point is going to be, so this is my reference, my datum, it will be minus mgl multiplied by cosine theta, right? Okay, now back to my overall Lagrange. We said L is equal to T minus V. So L is going to be equal to T, which was equal to how much? 1 over 2 m Vg squared plus 1 over 2 Ig theta prime squared minus the potential energy. So minus times minus is positive. So many students actually make the mistake here. When you have a minus and a minus, they will actually keep it as a minus. So make sure you don't make that mistake, and then keep track of all your computation. So this is my kinetic, this is my potential. So now we have the Lagrange. Now we can go ahead and then find our equation of motion. Recap. So this is what we're doing here. So we're doing d of dt dl d theta prime minus dl d theta is equal to t, right? Let's begin by this one. So partial derivative of Lagrange with respect to theta prime is going to be equal to, well, here, so you can simplify that. We said 1 over, I can do 1 over 2 theta prime square. We know Vg is equal to how much? L theta prime square, right? Yep, it's L square theta prime square plus theta prime square IG, right? Plus mg L cosine theta, right? So this is my, Vg is equal to L theta prime, right? Okay, so square it up, you'll end up with L squared theta prime squared, and then the last one is going to be equal to theta prime squared multiplied by Ig. Okay, so partial derivative of this guy with respect, oops, okay, sorry about that. So I'm doing this twice actually. Okay, so I can factor out theta prime squared alone, right? So if I do the partial derivative of this guy with respect to theta prime, right? What am I going to end up with? So, this guy, I'm not going to use this guy because it doesn't have theta prime, so it's very easy here. So I will only end up with theta prime multiplied by, so 2 and 2 will actually cancel each other. So L squared plus IG, and that's it, right? So this is that portion. Now, if I want to do dt of dl d theta prime, it will be what? Simply, I have theta prime, so I want to make this guy theta double dot L squared plus IG. That was the first part. Now let's look into partial derivative of Lagrange with respect to theta. So dl d theta is going to be equal to, so here we have nothing, then here we're going to have minus mg L sine theta. Okay, now back to my equation of motion, which is here. How do I do that? So this guy minus minus, so it's going to be this guy plus this guy, right? So it's going to be theta double dot L squared plus RG plus mg L sine theta is equal to t. So this is my forward dynamics of this 1 degree of freedom robot. And if you actually compare this guy with what we previously calculated, basically we have the same thing, right? This is based on Lagrange, and this is based on Newton, right? So we basically get the same results. So here is what. So when do you use Newton? When do you want to use Lagrange? So virtually all applications where you have multi-body, you want to use Lagrange. If you have 1 degree of freedom, very simple stuff, you can use this. For multi-body systems, normally you want to use Lagrange. Why? Because it will actually, so here it's obviously easier. You see, we literally two lines basically, versus Lagrange, we have, it's more involved. But for multi-degrees of freedom systems, Newton becomes very difficult. Why? Because you will actually have to incorporate your unknowns, right? OX and then O1Y, and then when you sum the forces, for example, on the second link, you will actually have a lot of internal stuff that you actually have to solve for before you can solve a direct relationship between the torques and thetas. Versus in Lagrange, let's say I have actually the same thing, but now I'm adding more stuff to it, right? So let's say I have this guy, right? Now let's say I have another one here and another one there. Okay, what happens now to this, right? So all I have to do is basically just express the potential energy of all of them, right? Which is very easy, right? So I can obtain the potential energy very simply, right? And then I can also obtain my kinetic energy. Why? Because I have, like x1, I have y1, and I have x2, y2, and then I have x3, y3. So from my homogeneous transformation, I know the coordinate of all these points, right? And therefore, I can find the kinetic energy of this whole robot, and I can also find the potential energy of this whole robot very easily. So my L is available. My Lagrange is always available if I'm using the homogeneous transformations. What really ends up with when you want to find the equation of motion for theta 2, for example, all you do is you just change how you are doing the partial derivative of your Lagrange with respect to whatever variable that you have. So it's very simple here, right? And when you are using Lagrange, basically, it's very simple. Like you don't need to, so the kinetic energy has to be absolute, but other than the kinetic energies, this guy doesn't have to be absolute here, right? So whatever theta that you have, you are good to go here. As long as L, when you are calculating your L, your kinetic energy has to be absolute, right? Same thing for rotation energies, right? Theta prime has to be absolute when you are actually, finding your Lagrange. All right, guys. So this really wraps up forward dynamics. Next time we're gonna have an example that we will do in MATLAB and then show you the implementation of this guy in MATLAB. Make sure, guys, you are following up on these lectures very well, and then try to do this on your own, and then make sure you are actually able to, get the same results using Lagrange and using, Newton. Try to, give yourself some challenge on your own, and then this is the best way for you guys to be able to learn it. And I posted one more assignment, and I would like you guys to work on that, and then try to work on it on your own, and then get to solve it by yourself. Any questions, guys, please do not hesitate to reach out to me by email, and then be very happy to set up a one-on-one Zoom call to be able to really explain to you whatever that is actually happening if you have more questions.